Okay, so we are going to make a slit. Let's do this, okay? I'm going to make two slits here. You see, there are two slits, one slit here, one slit. Let's say the distance between these two slits, okay? From the middle of this first slit to the middle of the center of the other slit. Let's say this is the distance D, represented by lowercase d. Let's put our screen over here. Here, okay? So this is our screen. Say this distance between the screen, okay? So this distance here, distance between the slit and the screen, this is L distance away. So we put some source of light here, and then what happens is the light, so you can make a dot, like dot here, right? Two dots, source. What happens is that, you know, light is going to go and then meet here somewhere on the screen, right? Let's call this is at a distance R1. This light travels a distance R1. And this light from here, this slit, right? So it's going to travel not R1 because this is going to go a little bit the other direction like this, so which means it's going to travel a little longer distance than R1. So it's going to go like that. And let's say this travel distance R2, okay? Now, this, and then let's say this point, some point P, alright? Some point P on the screen, okay? I want you guys to, so let's look at the center of this slit here. Center between this slit, I'm going to just make this dash 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 line here to represent this line. This line has the same length as this L, and let's call this as our, you know, if we have an origin here, our y equal to 0 here, okay? So we can call this as y equal to 0, okay? And then this point here is at some distance y rather than y equal to 0, it's at some distance. This point P is at distance y, okay? So this point P is at a distance y. Alright, this length is a y. So now so what happens here is light, right? So this is the important thing. Two light sources are going here, they are going to, you know, they are going to meet here. We don't know whether this spot will be bright or darker. What does it depend on, you think? Say that these lights have the wavelength lambda, okay? Wavelength of light lambda is traveling here. What does this depend on? Whether this point P will be bright or it will be dark region. So it turns out that we can use the same, you know, principle that we developed for interference of sound waves, right? So we said when these two waves they travel, and if the path length difference is a multiple of lambda, then wavelength, then this point will be constructive interference. The point here will be a constructive interference region if they meet, you know, there, but then the path length difference is a multiple of half of the lambda, right? Then this region, this point would be destructive interference, okay? So in this case, for the case of this light, it would be destructive, see, for the case of sound, constructive interference means you would hear a louder, right, sound. For the, and then the destructive interference means the region would be, we won't have any noise, right? It would be quite a spot. For the case of a light, again, here, if it goes to constructive interference, this point would be bright, it will have a high intensity of light. If it goes through destructive interference, that region would be totally dark, okay? So you see, for the case of sound, high intensity of sound, loud, right? For the case of light, high intensity of light means it would be bright, okay? So just making a connection there. Alright guys, so let's look at what's the path difference then here. One is traveling r1 distance, another wave is traveling r2 distance. Let's put a, I'm going to put a perpendicular distance from this point to this line here, r2, like this. So we have a perpendicular distance, okay? So this extra distance we have here is delta r. Well, really, yeah, delta r. That is the distance, extra distance traveled by the light from this slit, okay? Which means this is our path difference, okay? So one more thing, what shall I do is, let me see. So I'm also going to draw another line here. So this is going to be mostly the geometrical setup here. Okay, so guys, look at this carefully. So this is the center of, center point here. I'm gonna just connect this and then take it to this path. Now, important thing is this delta r, right? The path difference. If we had it from this point to this point here, y equal to 0, if we were to go there, this delta r would be really 0, right? Because both of the light would travel to the same distance. They would come like this, dot 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 here, dot 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 here, so there won't be any delta r. But this point P is not at this center y equal to 0, it's somewhere at distance y, okay? So r2 is traveling extra distance delta r than the light from this one, okay? This first slit here. Alright, so important thing to remember is condition for constructive interference is what? Path difference, right? In our case, this is delta. Did I write here delta r? Yes, delta r equal to m times lambda, right? Where m equal to 0, 1, 2, 3, etc. Okay, so this is m equal to 0 corresponds to this point y, which is exactly at a, it's, if you draw, at which the light from both of these slit travel equal distance. Okay, so let's call this as equation 1. Okay. So now I'm gonna just label some here. This point is P, right? Let me change the color. We make it blue. Let's call P, and then let us call Q. This center Q, and this point where we have y equal to 0 as R. Okay. I'm just calling this so it's kind of easy to look at the diagram. Okay. So in right angle triangle, triangle P, so this triangle I'm talking about, P, R, Q, we can look at what do we have here. In P, R, Q, we are given this length as y, right, and this distance as L, and then let us write this as angle theta here. Okay, if we have that as a theta, then we can use the trigonometry and we can write as a tan theta equal to what? So tan theta in this triangle as y by perpendicular by base, which is L here. Okay, so here we can rewrite this as y equal to L tan theta, equation 2. You'll see the reason why I have this right now. Okay, we'll use this in a few minutes. Okay, so this y is the position of the fringe. Okay, if it's a constructive interference, it's going to be a brightest spot. Okay, so that brightest spot would be at distance y from this center. Okay, that's what this equation tells us. Now we also want to look at this another small triangle, right angle triangle. This small one we drew earlier. This triangle we have. Okay, so I'm going to call this as a PQ. Let's call M N O, maybe not O, P Q R S T. Let's call it some. Oh my goodness! In physics, all the letters are taken for some important things. I don't want to confuse you guys with anything. Let's call some Z. Okay, zebra Z. Okay. So in triangle, right angle triangle M and G. In right angle triangle M and G, we can again, if we do the look at the geometry, it turns out, right, so these are two similar triangles, P, R, Q, and M and G. They are a similar triangle. By using a similar triangle, we can find that this 90 degree corresponds to this 90 degree. This angle is same as this, and then this angle corresponds to theta. Okay, so this tiny angle would also be theta. So now here we have what the information we have in this triangle is this. We have this hypotenuse, which is D, this base, which is delta R. Okay, so we can use what trigonometry here. Sine theta equal to what? Delta R by hypotenuse, right? So that's D. Okay, so I'm just going to rewrite this here because I have an equation here as a delta R, so I want to equate that at some point. Delta R equal to D sine theta. Okay, let's call this as equation 3. Alright, so here this equation is telling us what? So the path length between these two waves is delta R, which is equal to what? D times sine theta. Okay, D is the spacing between the slits, and theta is the angle, this angle, small angle here, right? Theta. Okay, so now this equation is telling us the path difference in terms of angle theta. This equation is giving us path difference in terms of the wavelength. But both of those equations are talking about the same path difference, so we must be able to equate those two equations. So I'm going to erase this part here, okay? So please take a moment to finish copying some of this, and then I'm going to erase this part. Okay. So I'm just going to write this down here. In place of, so equation 1 and 2, equating equation 1 with 2, we get this part must be equal to this m lambda, right? So I'm just going to write down here this d sine theta equal to m lambda. You have to write another step, okay? So you cannot erase on your notebook, so make sure you write this line here, okay? Alright, so here instead of sine theta, I'm going to write a subscript m to say that this m refers to the fringe m, okay? So Fringe, you may be wondering what is this fringe. So in the interference pattern you saw, right, there is a bright spot, dark spot, bright spot. So this sequence of this bright and dark, bright dark spot, they are called fringes. Okay. So m equal to 0 would be this point when y equal to 0. Okay. So directly at the if we pick a point between the center of the slit, and then if we make a straight line from that point to the screen, that point would be m equal to 0. Okay. Alright, so it means sine theta, so write sine theta m equal to m lambda, or sine theta m equal to m lambda by d. Okay, so this is, let's call this as another equation number 4. Now there is something called small angle approximation, meaning when this angle theta is very very small, then what we could do is this: sine theta m is equal to tan theta m. This is also equal to theta m. Okay, so make sure theta m is in radian. This is important to say that in is radian scale. Okay, when you do the calculation. Okay, so we can use this. So if we use this, this is called small angle approximation. If we do that, then it turns out we can write theta m equal to m lambda by d. Let's call this as equation 5. Okay. Now since this theta m is just m lambda by d, I want to go back to this equation 2. And wherever I have a tan theta, I can use this small approximation, just theta m. And in place of theta m, I will want to substitute with this. Okay. Sorry. So let's do that. So going back to equation 2. So substitute theta m into equation 2. Really, value of theta m into equation 2. Okay, that will give us what? We have a y equal to L. Tan theta would be just theta m, so it would be just m lambda by d. Now since we are talking about the specific m, so I'm going to put a subscript m here for y also. Okay, so ym equal to m lambda L by d. This equation gives the position of the bright fringe. Okay, position of the bright fringe in position of the bright fringe, nth bright fringe. Okay, so this gives the position of the nth bright fringe in double slit interference. Okay, so this is, let's call number 6. So this equation is very very important. Alright, so this means here we have some y. Let's say if it is y1, what happens? Instead of m, if it is a 1, meaning fringe number 1. Okay, so the fringe 1 would be what? If y equal to 0, this corresponds to m equal to 0. Okay, then m equal to 1 would be what? M equal to 1 would be somewhere around here, and that one would be what? y1 equal to 1 times lambda L by d. Okay, so that will tell us how far away that fringe corresponds to m equal to 1 from this center fringe. Okay, alright, so please take a moment to look at that. Okay, so what would happen? Let's see quickly, let's do this. So what would be the width of the fringe itself? To do that, what we can do is, let's look at for m equal to for m plus 1 fringe. Okay, what do we get? That is for m fringe. We will have y m plus 1 equal to what? Wherever we have m instead of m, we have m plus 1, and then rest of the thing ditto, lambda L by D, okay? Now let's see, that's equation 6, this is number 7. Now we want to find what is the width of the fringe itself. The brightest part we see would be small, tiny, or it would be big like this. That's the idea here. Then what we could do is just subtract this, ym plus 1. Subtract this ym from ym plus 1. Okay, so subtract. So equation 7 minus equation 6 gives us this here. Ym plus 1 minus ym equal to, let us call this delta y, meaning, the width of the fringe, which would be equal to what? This, right? This value here minus this. Look at this. If we multiply this inside here, what happens? Lambda L D times m plus we get lambda L by D, right? So since we will have m times lambda L by D here, we have a negative of m lambda L by D. Those two gets cancelled. So we are left with just lambda L by D, okay? So this one, let's call equation 8. So this delta y equal to lambda L by D. This will give us the width of the fringe itself. We'll talk a little more in the another video, okay?